And my Chinese name is Deng Shuan. I'm from PingCAP company, which powers TiDB. Before the talk, I'd like to do a survey about how many of you have heard about TiDB. Oh, cool. Okay. I will give the first, since some of you may not be familiar with TiDB, I will do a short introduction about TiDB, and then I'll talk about why we combine TiDB and Kubernetes together. Last, I will talk about how we make it possible to provision such a complicated distributed database on Kubernetes. Okay, first I will introduce TiDB. The TiDB architecture. TiDB is composed of three core components: the PD, the placement driver. It stores the cluster's metadata, and it has the God view of the whole cluster. It can it allow how to schedule the data between different between nodes, and the TiKV is the KV storage engine. It is based. It uses RocksDB internally, and we know that RocksDB is written by Facebook engineers, but it is a high performance single machine KV storage engine. TiKV combines the RocksDB and the Raft consensus algorithm. It's a little like etcd, but TiKV uses multi-Raft group, so it can store large amounts of data. And the TiKV is a distributed key value storage engine, and now it is hosted by the CNCF. And the TiDB component is the secular layer of the whole database. It's almost fully compatible with MySQL protocol. Users can use MySQL drivers to connect to talk to TiDB seamlessly. And for the TiDB it's a hybrid transactional analyzing database, the HTAP. But it also for the AP part, it uses the Spark. The Spark talk directly to TiKV without using JDBC to talk with TiDB. So it avoids the overhead of the SQL layer. And we have let's say about the TiDB ecosystem. As we have just saying that TiDB is the core components: PD, TiDB, and TiKV. And beyond that, we have used the open source monitoring and logging systems like Grafana and Prometheus for monitoring, and the Elastic Stack for logging. That's the TiDB whole cluster. For TiDB since TiDB is not alone, not a standalone solution. Users, most of our users have already stored their data on MySQL, and but MySQL is a single machine, single database. For large data, we have they are sharding solutions, but it involves the business logic. The application has to be adjusted for the sharding and for the sharding solution. With TiDB, we can use users don't have to worry about when their database or table becomes too large. It's just users just have to add more nodes for the compute load of TiDB or the storage node of TiKV. And there are many migration tools between TiDB and MySQL. For example, the loader which accept the MyDumper data format to load the MyDumper backup to TiDB, and we can also use the TiDB as a MySQL slave, which we can use the syncer for such use case for real-time synchronizing MySQL data to TiDB, and we also has a TiDB Lightning, which ingests the data directly to TiKV without the TiDB SQL layer. So it is much faster than the traditional tools like MyDumper or MyNoder. We also support binlog, which you can use to synchronize the TiDB data to other systems for analyzing and others. Then, since TiKV is cloud-native applications, the cloud-native applications has several features. First is it must be microservice architectured, and so it can easily be deployed on any cloud. It's not locked in any cloud vendor. Also, and the microservice architecture allows us to have elastic scaling, as we've just seen that the three core components can both scale horizontally. Also, the cloud-native applications, I think it should have high availability and easy automation operation. We all know that Kubernetes has become the de facto container orchestration system. Actually, Kubernetes, we can think of Kubernetes as a distributed cloud provider agnostic operating system. For example, we can think we know that Kubernetes has support the device plugins. So users can write drivers directly for Kubernetes, not just for the traditional operating system. And for container or pod, we can think of it comparably to with the traditional operating system process or thread. And for the Docker images, it's just like the traditional executable artifacts. And since pod and containers are just a single process or multi or threads, if they are stopped by any reasons, it will not restart it or recreate it. With deployment and stateful set, it's just like a system D or supervisor, like to automatically restart the service. And for the packaging system, Kubernetes also has the Helm, which is comparable to apt or YAM for easy installing applications on Kubernetes. Okay, Kubernetes also has at first, Kubernetes is a deployment stateless application deployment platform, and nowadays the Kubernetes is becoming has much powerful extensibility. It has the standard interface like CNI, CRI, CSI, and etc. For the scheduler, we can also extend the scheduler while user can specify their own scheduler or just write a scheduler extender to extend the built-in scheduler. And for the controller manager, we can write the CRD controllers to manage our own customized resources. And for API server, there's aggregated API server to extend the API server. The kubelet also has virtual kubelet, which can use apply the which is the serverless infrastructure, and for the cloud provider, they just need to implement the load balancer or persistent volume interfaces, so users can use this across all cloud. Okay. TiDB operator is the tool is the tool connect TiDB and Kubernetes. It's open sourced. You can check it here, and it has the following features. It can manage multiple TiDB clusters. In fact, our enterprise edition, we use TiDB operator to manage multi-tenant of TiDB clusters. So users can just deploy one TiDB operator to manage TiDB cluster for different users, and it can safely scale the TiDB cluster. While the stateful applications scaling is a bit cumbersome, and with the operator, we can safely scale seamless scale the TiDB cluster. Also, we provide the Helm chart, which users can just use the Helm chart to install the TiDB operator and TiDB clusters easily. We also support both local and network persistent volumes, and it also can start cluster with monitoring to aid the system administrators to monitoring the cluster for the DBA to monitor the cluster performance and to find the problems of TiDB cluster. And without this, the stateless applications on Kubernetes have has a failover feature. While the stateful applications, which most users will use stateful set to manage this stateful applications, it doesn't have built-in automatic failover. We also implemented in TiDB operator to automatic failover. And for rolling update, it can seamlessly upgrade the rolling upgrade the TiDB cluster without interrupt the user. And it also has the TiDB related tools integration. Here's the brief architecture of TiDB operator. Users just create a Helm chart and in TiDB in Kubernetes, then TiDB operator will watch our customer resource TiDB cluster for creating the related resources like stateful set of TiDB and the deployment of the monitoring system. Let's say the comparison of the built-in controllers. For stateless applications, now it's recommended to use the deployment. To manage these services. It supports all the features like start, scale, upgrade, and failover. But for stateful applications, usually the stateful application itself starts up is complicated. Different replicas start with different arguments, and so users have to do some tricks some hack to make the stateful application to run to bootstrap correctly. And for scaling, most stateful applications can't scale correctly with the stateful set. It's for example, the Elasticsearch, there's a built-in Elasticsearch YAML manifest, which user can deploy the Elasticsearch, but it can't scale. It only deploys 2 Elasticsearch pod. For scaling, because it uses the Kubernetes, then Kubernetes discovery, service discovery to add more load. And so besides the plain YAML manifest, someone wrote the Elasticsearch operator to manage the Elasticsearch service. Also, the upgrade, some stateful applications have some extra steps before upgrading. It's not supported natively in stateful set. And the failover feature is almost will not work for most of the applications. Then how do we implement this? As we all know, the operator or the customer controllers, the users can just embed the domain operation logic in their code to automatically manage your customized resources. There are 2 kinds of extensions. First, about the TPR or CRD. TPR now is deprecated, and the CRD customer resource definitions. Users can just create a customer resource just like the built-in deployment or stateful set. And users can write the domain operation logic in the CRD controller. But at first, it lacks schema and versioning. Now the versioning and schema is adding to the latest Kubernetes. There's also another extension called aggregate API server. It's complicated, but it's much powerful. In fact, we have implemented a aggregate API server for the TiDB operator, but since it is, but we found that it is too hard to deploy. It has to change the built-in API server's arguments, which is nearly impossible in public managed Kubernetes engines. Customer containers, users we define a custom resource definition called like this. The component, namely the PD, TiDB, TiDB, and others. It has image replica and resource limit or request and other fields. And the container just sync the when the container watches the spec changes, it will do the actual operation to keep the cluster look exactly what like the spec. It compares the status and the spec and gradually reconcile the resources to make them match. Here's our core interface, the manager. It syncs the TiDB cluster to create the corresponding stateful set and deployment pod stateful services config map and etc. Here's the custom resource definition of TiDB cluster. But we also encounter some problems with local PV, as we know that TiDB is IO-intensive applications, and the TiDB is already has the replication built in. At first, the Kubernetes doesn't support local PV, local persistent volume. It uses network persistent volume. We know that network persistent volume has replicas. Each data may store several replicas. When combined TiDB with network PV, it adds extra overhead for the data for the I/O. And here we consider the problems with local PV. If we want to maintain or the node B just fails, how will we do with local PV for stateful set? As for deployment, when the load fails, the deployment controller just creates another pod on other node. And also for the network PV, we can just create another. We can just stop the node and create another pod and bound the network PV to another node. But for local PV, we can't just do like that. So we just create another. We just increased the stateful set replicas and to make it like just 4. So the stateful set controller will create another TiDB pod, and the TiDB itself can internally synchronize the replicas to the newly created pod. But the node, the TiDB2 pod will become, if the node will never get up, come back, then the TiDB2 will be, become terminating or pending state. That's very annoying for users, but we still keeps the the running TiDB pod to three pod, which matches the user's expectation. And for the stateful set scheduling with local PV, here for if we want to deploy three TiDBs, like this. If node A is down, then there will it will lose 2 replicas, and the TiDB will out of service. So, but if we deployed more than 3 TiDBs, we can actually have this. This is acceptable since TiDB itself has a label, just like Kubernetes label. It can users can attach physical topology label to the TiDB store. So for this 2 TiDBs, it has node A label, and it has node B, node C. When PD schedule data, the same replicas would not scheduled on the same node as TiDB pod. So when the node A is down, we still has 2 replicas on node B and node C without so the TiDB is still in service. So this actually is based on our, we should consider our scheduling history. When we deployed the first 3 TiDBs, we just deployed, we must make sure that each TiDB should only be deployed on the load that doesn't have the same cluster's TiDB on it. And when the replica is great, when the TiDB pod is greater than 3, then we can do it's greater than 3 TiDBs, we should scan all the node and checking the previous TiDB and to decide if we can schedule the TiDB on the node A. So we implement this scheduler extender to do such advanced scheduling. This is impossible with the Kubernetes built-in scheduling policy. And there's another problems we encountered during our deployment. Let's consider such the following scenarios. If let's assume that if the node has 10 CPU, 10 memory, and 10 storage, 10 local storages, if one of the TiDB clusters TiDB consumes 4 CPU, 3 memory, and 4 storage. When the TiDB is upgrading, the stateful set will kill in the TiDB3 pod. Then the resource, then when the next pod scheduling, the resource would become 10 CPU and 10 memory. So there might be a chance that another cluster's TiDB or other recent pod would schedule on this load because it can still assign. It still has 8 CPU and 5 memory, 6 storage on this load. But when the newly created TiKV pod should, since it has the local PV bound on this node, it must be scheduled on this node. Then, but it doesn't have the required resources. So this TiKV would be always pending. How do we resolve this? We have advanced scheduling based considering the virtual resources. For this, we have the local PV, and we can find its PVC, and we can find the PV's bounding PVC, and then the bounding pod, and we should check that we can know that the bounding pod has the 4 CPU and 3 memory. We would reserve at least 4 CPU and 3 memories for when other pod is scheduling on this load. So they still have 4 CPU and 3 memories occupied. When the TiKV another pod is scheduling on this, we should only say 6 CPUs and 7 memories. So we can't schedule this other pod on this node. So this is actually because the local PV and the Kubernetes built-in stateful set is mainly for the it's was first designed for network PV, so it doesn't consider such scenarios. So there still has many scheduling problems with this with local PV, and we do much effort on this.